I'm Wil McCarthy, Futuresmith. I'm the author of Rich Man's Sky and other science fiction novels. You can find out more at futuresmith.com. So called hard science fiction is fiction where the science is correct, or at least sounds correct enough to satisfy a demanding audience. In this series, we'll explore how I've used simple calculations in a spreadsheet program to work out technical details for science fiction novels like Rich Man's Sky. Hi, and welcome to another exciting episode. Uh, Today, we're going to be talking about kinetic impact, the kinetic energy of an impacting object. So, to do this, we have two equations that we're going to be using. One of them is kinetic energy. We've seen this one before. The kinetic energy of an object is equal to 1 half mv squared. That's zero point 0.5 times the mass of the object times the velocity of the object squared. Um, and then we have a second equation here, which is the diameter of a crater that's made by an impacting object. That diameter is equal to the cube root of the kinetic energy times a conversion factor of 4.65 times 10 to the minus 17th. So if the kinetic energy is measured in joules, this expression will give us the diameter of the crater in kilometers. So what does this look like? We'll start with a simple example, which is a BB. I think many of you have probably fired a BB gun or watched someone else. So the mass of a BB is about zero point 0.3 grams, not a very heavy object, and its velocity in meters per second is about 100 meters per second. If you get shot by a BB gun, it will sting, but it may or may not break the skin. Um, This gives us an energy in joules of 1 half mv squared. This is 1 half mv squared of 1.5 joules, so not a lot. Um, and that impact is not very much like an explosion, so we'll ignore this column. We'll ignore these columns here. Uh, Oops. We'll ignore these columns and we'll go straight to the crater diameter in centimeters. We talked about how we calculate our crater diameter in kilometers. We simply divide that by 1,000 to get meters and divide again by 100 to get centimeters. Um, what we see here is that if we fire a BB, and this crater diameter is assuming we're striking something like sandstone or concrete, uh, something with about the consistency of a fragile rock. Uh, and what we see is we get uh, a crater of about less than half a centimeter. So we're getting a ding, a little chip in the concrete that's about the size of the BB itself. And sometimes, the BB might not leave a mark at all, uh, depending on a number of factors. Um, Now we can size this up. We can look at a uh, bullet fired by an AK-47, for example, and uh, that gives us a weight of about 10 grams and a muzzle velocity of about 800 meters per second. This gives us a kinetic energy of 3,000 joules. And over here, the crater diameter in centimeters uh, of about 5.3 centimeters. So you can knock a pretty good sized hole in some concrete, uh, or rather make a good sized chip out of it using a 7.62 millimeter bullet. Um, if we scale up then to a 50 caliber machine gun bullet, the diameter of the crater jumps to about 10 centimeters. And if we look at orbital debris, if we imagine that we have an object weighing 1 gram that's traveling at the velocity of low Earth orbit, which is 8,000 meters per second, um, that orbital debris, if it hits concrete or the equivalent of it, will make again about a 10 centimeter dent. So that's all very impressive. Um, Now, for those of you who remember Jerry Pournelle, he was a science fiction writer who proposed a kinetic energy weapon that would orbit the Earth. It was a bunch of flying crowbars. They'd orbit the Earth and then they'd vector in aerodynamically on whatever target you chose, um, with a mass of about 100 kilograms. And again, if these are traveling at orbital velocity, uh, then they'll leave a crater about 90 meters across. Oh, I'm sorry, reading the wrong row there. About 5 meters. Uh, so to destroy a target, you would need a number of Cornell's flying crowbars, and that's consistent with his writings on the subject. Uh, you can see I've used yellow highlighting to highlight the units that are of relevance to us here. Interestingly, one Cornell's flying crowbar that strikes the ground at 8,000 meters per second has an explosive equivalent of about a ton of TNT, about 75% of a ton of TNT. So that'll give you an idea of what that impact is like. It's much more like an explosion than it is like a BB striking a surface. Um, Now, similarly, if we crash the International Space Station, now obviously the International Space Station is mostly hollow, and if it hit the atmosphere, it would slow way down, it would burn up, and it would hit the ground. Whatever remained would hit the ground at a velocity a lot slower than 8,000 meters per second. Um, but let's ignore the atmosphere. Let's imagine we're hitting the moon with an object the size of the International Space Station, uh, and the atmosphere is not a concern. In that case, we'll get our crater of about 90 meters across. Um, so that's a pretty substantial explosion. It's equal to about 3 kilotons. Uh, so we're talking about a kind of a small atomic bomb level here of explosive force. Now, for those of you who've seen Meteor Crater in Arizona, that's a crater that is about 1.2 kilometers across, and it was made by a meteor weighing about 1 times 10 to the eighth kilograms, going about 29,000 meters per second. That's science's best guess as to the characteristics of the Barringer meteor. And you'll see, in addition to making a crater about 1.2 kilometers across, a meteor with those characteristics gives you about a 10 megaton explosion. So this is a city killer here, a meteor this size. If we go up to something even more ferocious, Halley's Comet um, weighs about 2 times 10 to the 14th kilograms. And at perihelion, at its closest approach to the sun, um, it's going about 50,000 meters per second or 50 kilometers per second. Um, at the Earth, at Earth's orbit, it's not going quite that fast. But let's just imagine this very fast moving comet. That gives us an explosive equivalent of 63 million megatons, 64 million megatons. So that's 64 teratons of explosive force. And that gives us a crater that is more than 200 kilometers across. Uh, so this isn't just a city killer. This is a mass extinction event. This is a dinosaur killer here. Uh, this actually would be even more damaging than the meteor that killed the dinosaurs. That gave us a crater that was uh, certainly less than 200 meters across or 200 kilometers across. Um, about 180 kilometers, if memory serves correctly. And then there's an asteroid called Pallas out in the asteroid belt that weighs 2.1 times 10 to the 20th kilograms. And if we imagine that hit the Earth at sort of a cometary velocity of 30,000 meters per second or 30 kilometers per second, that would give us a crater diameter of more than 16,000 kilometers. Now, the Earth is only about 12,000 kilometers across. Uh, so this would completely obliterate the Earth. Um, so this table gives you kind of an idea of what different impact events are like, uh, and how you can use them in fiction. I've used the yellow highlights to show which of these units make sense to mention in fiction. Uh, with the city killer asteroid, really the most meaningful thing to say about it is you've got a 10 megaton explosion and a 1.25 kilometer wide crater. Uh, if you're talking about a BB, the thing that makes the most sense to say is it leaves a chip that's roughly the size of the BB itself. Uh, and in the case of the planet killer, the most relevant thing is it kills the planet. Um, Now we can get cute with this. We can apply these same uh, equations to a cosmic ray particle. Imagine we have an iron nucleus traveling at half the speed of light. Uh, this gives us a kinetic energy of much, much, much less than a joule, and it gives us a crater diameter that's a tiny, tiny fraction of a centimeter. And what this tells us is that the damage from a cosmic ray isn't caused by it gouging a little crater in our skin. Um, the reason cosmic rays cause such havoc in living creatures is because they're ionizing. So you've got this particle that's traveling through your body uh, that's charged, and it damages molecules on its way through. Um, the reason I'm using half the speed of light and not, say, 9/10 of the speed of light is that we don't want to worry about relativistic effects here. As we approach the speed of light, the kinetic energy increases exponentially. Uh, and if we were somehow to reach the speed of light, the kinetic energy for any real object would be infinite. And we don't want to worry about that here in this science fiction story we're telling. But what we can do, for example, is we can take a BB. Let's copy it down here. And let's say we have a BB that's traveling at half the speed of light. Well, what does that do for us? That gives us a uh, explosive equivalent of about 700, 800 tons of TNT. So we're getting close to a megaton, or a kiloton rather, uh, of explosive force. Um, and the crater that we see from that is about 54 meters across. So a BB traveling at half the speed of light is not a city killer, uh, but it certainly will take out a city block uh, very handily. But let's say that instead of a BB, let's try one of Cornell's flying crowbars. Let's paste that in. Clipboard error. No, thank you. All right. In that case, if we have a 100-kilometer crowbar or 100-kilogram crowbar that's traveling at half the speed of light, that gives us a crater diameter of about 3.75 kilometers. So this is definitely a city killer, a weapon like this. Um, so this shows you how to build a little calculator that you can use to decide in a science fiction story if you have a mass striking uh, a planet, uh, what kind of effect, or a building, or a city, what kind of effect you can expect that mass to have. So that's our lesson on kinetic impact. I hope you found it interesting. Thank you. Bye bye.